Hello friends, welcome to you all on my YouTube channel JK Academy India. In this video, we will discuss about the starting torque of three-phase AC induction motor and the relation between the torque and the rotor power factor. It has been shown that in case of a DC motor, the torque is proportional to the product of armature current and the flux per pole. Similarly, in case of an induction motor, the torque is also proportional to the product of flux per pole and rotor current. There is no more factor that has to be taken into account. The power factor of the motor is cos phi 2 rotor. Therefore, torque is proportional to phi I2 cos phi 2, or we can say it is K phi I2 cos phi 2. I2 is the rotor current at standstill when motor is not running at start point, or we can say before switching on t is equal to 0 plus time. Phi 2 is the angle between rotor EMF and rotor current, and K is a constant denoting rotor EMF at standstill by E2. So E2 is proportional to phi. Therefore, T will become K1 E2 I2 cos phi 2, where K1 is another constant. The effect of rotor power factor on rotor torque is illustrated in this figure. So this is the pole pitch and this is the average torque shown by dotted line. For various values of phi 2, from the above expression for torque, it is clear that phi 2 increases and hence cos phi 2 decreases. Means flux in the rotor increases, its power factor, rotor power factor decreases, and vice versa. In the discussion to follow, the stator flux distribution is assumed sinusoidal. This is the flux wave. The revolving flux induces in each rotor conductor or bar an EMF whose value depends on the flux density in which the rotor conductor is lying at the instant considered BLV volt. Hence the induced EMF in the rotor is also sinusoidal. So this is the waveform of induced EMF. Now there are two assumptions. First, rotor assumed non-conductive, so phi 2 will be 0. In this case, the rotor current I2 is in phase with EMF E2 induced in the rotor. The instantaneous value of torque acting on the rotor conductor is given by the product of instantaneous value of flux and the rotor current, because force is proportional to B I to L. B is the flux density, I2 is the rotor current, and L is the length of the rotor. Hence, torque curve is obtained by plotting the products of phi, flux phi or flux density, and I2. It is seen that the torque is always positive, that is in unidirectional. Now let's assume that rotor is inductive. In that case, I2 current flowing through the rotor will lags behind EMF E2 by an angle phi 2, that will be tan inverse of X2 by R2. R2 is a rotor resistance per phase, where X2 is a rotor reactance per phase at standstill. This is the rotor reactance per phase, this is the resistance per phase, and this will be the impedance per phase, and this will be the angle, and cos phi 2 is the power factor of rotor. It is seen that for a portion AB, for this section, the pole pitch, the torque is negative for this time period. The torque is negative, hence the total torque, which is the difference of the forward and the backward torque, is considerably reduces. If phi 2 equals to 90 degree, then the total torque is 0. Here the flux is considered 90 degree, not flux, phi 2 angle. Angle is being considered 90 degree. That time torque is almost 0. Total torque at this moment. Because in that case the backward and forward torque become equal and opposite. Now let us see the starting torque. The torque developed by the rotor at the instant of starting is called starting torque. In some cases, it is greater than the normal running torque, whereas in some other cases, it is somewhat less. Let E2 is the rotor EMF per phase at standstill, R2 is the rotor resistance per phase, and X2 is the reactance per phase at standstill. Then the impedance Z2 will be this per phase at standstill, and the rotor current I2 will be E2 by Z2, where the cos phi 2 power factor will be R2 by Z2. At standstill, the starting torque can be written as K1 E2 I2 and cos phi 2. Putting the value here of I2 and cos phi 2, we will get K1 E2 square R2 by R2 square plus X2 square. If the supply voltage V is constant, then the flux phi and hence the E2 both are constant. So K2 is some other constant. We can rewrite the equation of starting torque as K2 R2 by Z square. Now K1 is 3 by 2 pi by Vs. Therefore, starting torque will become this, where Ns is the synchronous speed in revolution per second. Starting torque of a squirrel cage motor. The resistance of a squirrel cage motor is fixed and small as compared to its reactance, which is very large typically at the start because it stands still. The frequency of the rotor current equals the supply frequency. Hence, the starting torque I2 of the rotor, through very large in magnitude, lags by a very angle behind E2, with the result that the starting torque per ampere is very poor. It is roughly 1.5 times the full load torque. Although the starting current is 5 to 7 times of the full load current, hence such motors are not useful where the motor has to start against heavy loads. Now the starting of a slip ring motor. The starting torque of such a motor is increased by improving its power factor by adding external resistance in the rotor circuit. We have seen that the starting torque is equal to K2 by R2 by Z2 square. So if we are increasing the rotor resistance, the starting torque will increase. So for the starting, we have to improve its power factor by adding external resistance in the rotor circuit. The star connected rheostat or the rheostat resistance being progressively cut out as the motor gathers speed. Addition of external resistance, however, increases the rotor impedance and so reduces the rotor current also. Because if we are increasing the rotor resistance, Z2 will also increase, because Z2 is nothing but square of R2 plus X2 square. Hence, starting torque is increased, but after a certain point, the effect of increased impedance predominates the effect of improved power factor, and so the torque starts decreasing. Now the condition for starting torque, we know the formula for the starting torque. If we differentiate it by this with respect to R2, and it should be 0. So you may know the differentiation of U by V, or the differentiation of Z by X. So I will give you the differentiation of d by dt of U by V. So in this case, first, this term means 1 upon V is remain constant, and differentiation we do first numerator term, then minus the lower term or the square of the lower term, and differentiation of the second term. So this is the method to differentiate this term. First, the denominator will be taken as a constant, differentiating with R2 with respect to R2 will be 1. After that, putting R2 as a constant, 1 upon R square x square will be the whole square differentiation, and again we have to differentiate R2 square, so it will be 2R2. Finally, R2 square plus x2 square will be 2R2 square, and from this we will get R2 equals to x2. So this is the condition to get the maximum starting torque, that the rotor resistance should be equal to the reactance of the rotor. Effect of change in supply voltage on starting torque. We have seen that starting torque equation contains E2 square, and E2 is proportional to the supply voltage. Therefore, T starting can be written as K3V square R2 by Z2 square, where K3 is another constant, and hence starting torque is proportional to the square of the applied voltage. So clearly, the torque is very sensitive to any changes in supply voltage. A change of 5% in the supply voltage will produce a change of approximately 10% in the rotor torque. So in this video, we have discussed the starting torque and the condition of starting torque, and how to get the starting torque by adding the external resistance in case of slip ring induction motors to get the high starting torque, and the effect of supply voltage on the starting torque. So thanks for watching. We will meet in next video. Take care and goodbye.